Good afternoon viewers and welcome to the EduSat Live lecture for the science stream. This lecture is regarding chemistry and we have with us Dr. K.K. Arora, who is an associate professor at Zakir Hussain College of University of Delhi. Dr. Arora has a vast experience of 32 years and has written 8 books on several topics. Previously, he has taught about carbohydrates, monosaccharide structure, representation and stereochemistry. Also in this lecture, we will start with the determination of ring size and he will also introduce disaccharides and polysaccharides. So over to Dr. K.K. Arora.
Thank you. Hello viewers. In our previous sessions, I have discussed about the classification of carbohydrates and then structure of monosaccharides, especially glucose has been taken in details. So in our today's session, first we will briefly review what we had done till now. Then we shall talk about that how the size of the ring in these carbohydrates, particularly monosaccharides, was determined, and then we will move on to the disaccharides. We will not take up the method by which the structures of these disaccharides have been determined. We shall just talk about their structures and their representations. Specifically, we will take the examples of maltose, lactose and sucrose. And then amongst polysaccharides, we will talk about the structure of starch, cellulose and glycogen. And finally, I will summarize my today's work. So, till now we have discussed that glucose is a molecule which consists of 6 carbons. These carbons are attached in straight chain. One of the carbon is present as aldehyde, whereas it has 5 hydroxyl groups. Since it contains 4 asymmetric carbon atoms, so 16 isomers are possible for it. Then on the basis of certain reactions, Fischer gave a specific configuration for it, that how these hydroxyls on these asymmetric carbon atoms are arranged. And then it is represented in Fischer projection like this. This is the open chain structure for glucose, and especially we call it as D plus glucose because it is dextrorotatory and it has D configuration. Then certain observations were made which could not be explained by the open chain structure of glucose, and a cyclic structure was assigned to it, in which it was said that one of the hydroxyl group from the chain joins with the aldehyde group at carbon number 1, and this molecule exists as a hemiacetal type of structure. And when a new asymmetric carbon atom is formed here, which was earlier in the form of C double bond O, then 2 isomers are possible which are called anomers. This is the representation of alpha anomer, which is represented in Haworth projection like this, and then its exact conformation, it is written like this, and it is an alpha isomer. This hydroxyl occupies this axial position which is going downward, and similarly beta isomer of this glucose is represented like this, where this hydroxyl at carbon number 1 is placed on the left hand side. This is the Haworth projection, and this is the conformational representation where the hydroxyl group at carbon number 1 occupies this equatorial position, and in Haworth position it is going upward. We introduced the word pyran in this because this is a 6-membered ring structure and it is given on the basis of a 6-membered organic compound which contains 1 oxygen, and its name is pyran. So we call these as pyranose on this basis. So this is all what we have done. But earlier this 6-membered ring structure was given arbitrarily because most of the compounds are having 6-membered ring structures are more stable. But this molecule can have a 5-membered ring structure if hydroxyl at carbon number 4 is involved, and it can have even a 7-membered ring structure if hydroxyl at carbon number 6 is involved. People tried to determine the ring size of this carbohydrate at that time. This is the time when I was talking is somewhere in 1890. So no instrumental methods were available at that time, and only chemical reactions were used for all this. So no good reaction could be used for determining the ring size of monosaccharides themselves. but we obtain glycosides, which also we have discussed earlier. They have acetyl type structure here, so that ring is blocked in a way and it cannot be opened easily. So, ring size in glycosides was determined. We have discussed that glycosides are the compounds which are obtained by reaction of these monosaccharides with alcohols. Now, the sugar part forms the glycoside and the other alcoholic part is called aglycone, and the linkage is called glycosidic linkage or glycosidic bond. We represent like this. Suppose this is any monosaccharide having a hydroxyl group, this is the anomeric carbon. When it reacts with methanol, so an acetal is being formed, because this is an hemiacetal type of structure. This is acetal being formed, and this bond, that is the bond between this oxygen and the sugar moiety, this bond is called glycosidic bond or glycosidic linkage. Now, glycosides exist in nature also. There are many phenolic naturally occurring compounds which remain attached to different monosaccharides. Say this is one example that I have taken. This is called glucovanillin. Actually, this molecule is vanillin, which has this hydroxyl group. It is a phenolic hydroxyl. It acts as a glycone and combines with this glucose molecule. When it is hydrolyzed, we get glucose and this vanillin. Vanillin, you know, is used for vanilla flavor in many food items. It is obtained from plants, particularly vanilla flower. Now, when we try to determine the structure for this glycosides, in 1893, Emil Fischer, he prepared methyl glucoside by treating glucose with methanol in presence of HCl, and he refluxed it. That is, he heated this and he obtained a glucoside, and he gave arbitrarily a 6-membered ring structure to it. Then in 1894, Eckenstein was working on it, and he found that the compound that we obtained by treating glucose with HCl is not a single compound. It is a mixture of 2 isomers. So, he isolated the second isomer, and these 2 glycosides, since they are obtained from glucose, that is why we are calling them as glucosides, they were called normal glucosides, because this is the representation of 6-membered ring structure which was arbitrarily given, and this is the glucoside formed with hydroxyl on the right side, we call it as alpha, and one with the hydroxyl on the left hand side is called beta, and they have formed the methyl glucoside. So, in place of OH of the original glucose, now it is OCH3 in these 2, and they are named as methyl alpha D glucoside and methyl beta D glucoside. But in 1913, again Emil Fischer found that 2 more glucoside could be obtained from glucose when glucose was mixed with methanol and kept at 0 degree Celsius in presence of 1% hydrochloric acid. This reaction was actually never used for the preparation of glycosides before, but it was just kept, and they found that something has been formed, and they found that 2 new compounds are there. They behaved like glucosides, but they were different from the glucosides which are obtained by heating. So, now we have got, it means 4 glucoside from glucose. 2 are called normal glucosides which are obtained by heating process, and 2 others which are obtained under cold conditions. Actually, Haworth and Hurst, these were the scientists who gave a sequence of reaction in 1927 by which ring size could be determined, and they assigned a 6-membered ring structure to the normal glucosides and a 5-membered ring structure for the other glucosides which are formed under cold condition. Now, let us discuss what was the reaction sequence they used. They took D plus glucose, treated with methanol in presence of HCl, refluxed, they obtained glucoside, we call it as methyl D glucoside. Then they treated it with dimethyl sulfate in alkaline medium. Now, what happens when compound containing hydroxyl groups are treated with dimethyl sulfate? Methylation occurs, and it was found that the product which was found had 4 more methyl groups. So, it was named as methyl tetramethyl D-glucoside. We are writing these two methyls separately just to indicate that this is the methyl which is present initially in glucoside. Then it is hydrolyzed by HCl. Now, on hydrolysis what happens? Again this glycosidic linkage breaks, and that this methyl that was written separately is lost, and we get tetramethyl D-glucose. This tetra-dimethyl glucose was oxidized with bromine, a lactone was formed. We have discussed how this lactone is obtained earlier while we were discussing the structure determination for glucose. And then this lactone on oxidation gave a particular compound, trimethoxyglutaric acid. This is the structure for trimethoxyglutaric acid. It is a 5 carbon dicarboxylic acid with 3 methoxyl groups. Now, using the structure of this compound, they went back in the reaction sequence and they assigned it a 6-membered ring structure. We will take the reaction sequence considering a 6-membered ring structure. Say it is the carbon at number 5 where the hydroxyl present on this carbon has formed the hemiacetal linkage with the aldehyde group, and this is now a 6-membered ring structure. We call it as a normal glucoside. This is treated with methanol, HCl, and we refluxed. This is the glucoside it is formed. Here I have not shown here the alpha or beta because I am showing this on the one side. So, it can be both the anomers. Then it is treated with dimethyl sulfate. Now, there are 4 remaining hydroxyls, 1, 2, 3 and 4. So, they will get methylated and we will get this compound which we called as methyl tetramethyl, 1, 2, 3 and 4. These hydroxyl groups, they get methylated here. Then in the next step, this tetramethyl derivative is hydrolyzed with HCl. Now, what happens in HCl? These are the ether bonds, they will not dissociate, but this is an acetal bond. This breaks up and this methanol molecule is lost, and again we get OH here. So, again we have now hemiacetal. Now, till now what we have done, in a way we have blocked all other hydroxyl groups as methoxin, and only that hydroxyl is free which was present earlier in the hemiacetal form. It is again here shown as a hemiacetal. Now, it is oxidized with bromine water. Now, what will happen? This ring will open up, this will become CHO, that is aldehyde, and then aldehyde will be oxidized by bromine water into carboxylic acid, and this carboxylic acid again form a cyclic ester with this hydroxyl when on heated to 90 degree, and these cyclic esters are called lactones. So, this is the lactone that we get. It is now C double bond O and then the other part of the chain attached here. So, what we have done? We have started with glucose, prepared its methyl glucoside, then blocked all other hydroxyl groups on treatment with dimethyl sulfate, then hydrolyzed back and then oxidized the aldehyde group to carboxyl and then converted into lactone by heating it to 90 degrees Celsius. Now, this lactone was oxidized. Now, on oxidation what happens? This bond breaks, this becomes back COH and this becomes OH back. And what nitric acid does? Now, nitric acid cleaves the molecule where the 2 neighboring carbons, they have got this hydroxyl group and then oxygen function, and this carbon gets converted into carboxyl group. Now, nitric acid can break on this side also, because this is also on the other side of the hydroxyl. When the cleavage occurs here where I have not shown the dotted line, then we will get a 4 carbon compound, and if it cleavage occurs here we get a 5 carbon compound. Now, had the hydroxyl of carbon number 4 being involved in the ring formation, that is 5-membered ring, then we will not get this 5-membered derivative. We can get this when the linkage is on to hydroxylase at carbon number 5, linkage is on to this side and cleavage may occur here and cleavage may occur here. So, we will get a 4 carbon dicarboxylic acid and a 5 carbon dicarboxylic acid, and actually that were obtained. So, on this basis a 6 membered ring structure for this normal glucoside was confirmed. Now, we can represent this by taking the this open chain structure. This is carboxyl here, these are the 4 hydroxyls which are converted into methoxyl. If linkage was from this carbon, that is the 6th carbon, then this will be free now. And now when it is oxidized with nitric acid, what will happen? Only this will be oxidized into carboxyl, no cleavage will occur. So, it means if originally a 7 membered ring structure was there, then we will get this 6 carbon dicarboxylic acid with 4 methoxyl groups. We cannot get a 5 carbon dicarboxylic acid. So, we can get 5 carbon dicarboxylic acid only if this carbon number 5 is involved in the ring formation here. This is represented in the Haworth projection. This is D plus glucopyranose. I have shown the VV line here that I am not taking the alpha or beta ionomer, it can be any of these. This is the hemiacetal structure. On treatment with methanol, it is now acetal structure, we call it as methyl D plus glucopyranoside. Here I have taken the full names. Then methyl D plus glucopyranoside treated with dimethyl sulfate. Now, all these 4 hydroxyls 1, 2, 3, 4, they get converted into their methyl ethers, and we give a correct name to this compound as methyl 2,3,4,6 tetra O methyl. In order to differentiate, because for this methyl we are using a term in the end as side, glucoside, and these are attached through oxygen. So, that is why we write a capital O before it, that 2,3,4,6 tetra O methyl. Then it is D configuration D, dextrorotatory compound plus glucopyranoside. Then this compound is now hydrolyzed with HCl. Again this acetal bond will break, it will become OH, but all these methoxyl group will remain as such, and this compound will be named as 2,3,4,6 tetra O methyl D plus glucopyranose. Now, it is not pyranoside because it is no longer glucoside, it is now the cyclic structure for the glucose. So, that is why you are using glucopyranose. This is oxidized by bromine water. So, this ring opens, this becomes aldehyde, then again ring formation. So, this becomes a cyclic ester, that is the lactone, and we call this compound as 2,3,4,6 tetra O methyl D gluconolactone. And then this lactone is finally oxidized with nitric acid. Now, what will happen? This opens up, this is the hydroxyl present at carbon number 5 now, and bond may break on this side or this side. So, we may get a 4 carbon dicarboxylic acid, or if this breaks here, we get this 5 carbon dicarboxylic acid. Since this compound can be formed only if the linkage is through carbon number 5, so that confirms it a 6 membered ring structure for the normal glucosides. Then the glucoside formed at 0 degree Celsius, that is which were not the normal glucosides. They repeated the reaction sequence in a similar way, that D plus glucose was taken, mixed with methanol and HCl at kept at 0 degree Celsius. The compound obtained methyl D glucoside treated with dimethyl sulfate in presence of NaOH. We get methyl tetramethyl D glucoside hydrolyzed with HCl, tetramethyl D glucose is obtained, oxidized with bromine water and heated, lactone is obtained, and this lactone is oxidized by nitric acid. In this case, a compound dimethoxysuccinic acid, are also called as dimethyl tartaric acid, this is the compound that was obtained. This is 4 carbon acid, dicarboxylic acid with 2 methoxyl groups. So, this is, we can also call it dimethoxysuccinic acid or dimethyl tartaric acid, because tartaric acid has got 2 hydroxyl group in it. Now, on this basis it was assigned a 5 membered ring structure, and by drawing a 5 membered ring structure, let us see how this compound is obtained. If hydroxyl at carbon number 4 in the glucose is involved in the ring formation, and this is now hemiacetal structure here, we will have this 5-membered ring structure, 1, 2, 3, 4 carbon, and 5th is this oxygen. On treatment with methanol, a glucoside is formed here. Then on treatment with dimethyl sulfate, these hydroxyl groups 1, 2, 3 and 4, they get methylated, we get tetramethyl derivative. Then this tetramethyl derivative is hydrolyzed back with HCl, this acetal bond breaks and we get the hemiacetal and again cyclic structure CHOH. Then it is oxidized with bromine water, this is oxidized into carboxyl and then lactone formation. So, this is the lactone 5-membered ring structure, and this on oxidation with nitric acid will give this compound. Now, what will happen when we treat it with nitric acid, this breaks up and this becomes OH here, and with nitric acid cleavage may occur onto this side or onto this side. When it cleaves on this side, we will get 2 molecules of 3 carbon each. If it cleavage occurs here, then we will get a 4 carbon dicarboxylic acid and a 2 carbon fraction. So, this was the basic reaction which could be used to differentiate between a 5-membered ring structure or a 6-membered ring structure, because in no case if a 5-membered ring structure is there, we can obtain a 5-membered dicarboxylic acid, we cannot obtain, and if it is a 7-membered ring structure, again also we cannot get a 5-membered ring structure. So, a 5-membered dicarboxylic acid that was obtained, that confirmed that ring structure was 6-membered in the normal glucoside, and here we are getting a 4 carbon dicarboxylic acid that indicates that it is a 5-membered ring structure in it. We can represent this in the Haworth projection also. This is the representation of 5-membered ring structure. This is the anomeric hydroxyl, this is the carbon which was present earlier as the aldehyde. When it is treated with methanol and HCl, this will be present as now acetal linkage, and we call it as methyl D-glucofuranoside, because it is a 5-membered ring structure matching with furan, we call it as furanoside. Then this is treated with dimethyl sulfate. All these hydroxyls they get methylated and we get methyl 2,3,5,6 tetra O methyl D-glucofuranoside. This indicates the position where the hydroxyls were there. Since the hydroxyl at carbon number 4 is now involved in the ring formation and 5th and 6th carbon hydroxyls are available, so they get methylated. Then this is hydrolyzed with HCl, this again becomes the anomeric hydroxyl and we get 2,3,5,6 tetra O methyl D-glucose. This is oxidized with bromine and then heated. This is oxidized into carboxyl group and then forms a lactone here. We get a 5-membered ester which on oxidation with nitric acid gives us this dimethyl tartaric acid or dimethoxysuccinic acid. So, based on this reaction sequence, the ring size was established in the glucosides. Then one more method was developed which was easier than this, that involves the oxidation with pyridic acid. Pyridic acid is very specific in its oxidation, that it will cleave a carbon-carbon bond where both the carbons have got oxygen function like alcohol or aldehyde or ketone, but it does not cleave the bond where one carbon carries some ether function. Such as in this compound, this pyridic acid will cleave here, and wherever the carbon-carbon sigma bond is cleaved, each carbon gets 1 hydroxyl. So, this carbon will get 1 more hydroxyl and 2 hydroxyl will eliminate water, will become C double bond O. So, it will be converted into aldehyde. From this side I have shown both the alkyl groups, 1 more hydroxyl will come, they will eliminate a water molecule, will become C double bond O and we will get ketone. Means different compounds which have hydroxyl groups on the neighboring carbon, we call them as vicinal diols, will be cleaved by pyridic acid to give aldehydes or ketones. If they are not on the neighboring carbon, like a diol is like this, CH2OH, CH2, CH2OH, neighboring carbons do not have hydroxyl group, then these are not cleaved by periodic acid, no cleavage occurs. Even if some ether linkage is there, like it is CH2O CH3 and next carbon has the hydroxyl, even then this bond will not be cleaved by periodic acid. So, periodic acid cleavage is very specific, and this was used to determine the position of hydroxyl group, that which is involved in the ring formation. Suppose we have this type of compound where 3 carbons are there, each of them have 1 hydroxyl. Now, periodic acid will be able to cleave this bond as well as this bond, and as I told you that each sigma bond between 2 carbons, when it breaks, each of the carbon gets 1 hydroxyl group. So, what will happen? This carbon gets 1 more hydroxyl and then loses a water molecule, ultimately we will get aldehyde. This will get 1 more hydroxyl, will lose a water molecule, will be converted into a ketone, but this carbon will get 2 more hydroxyl, 1 from this side, 1 from this side, will lose a water molecule and will give us a molecule of formic acid in this case. So, ultimate products now can be, if there are more than 2 hydroxyls in sequence, some of the molecules may be oxidized into formic acid or some aldehydes or some ketones. Let us take the example of glyceraldehyde, that is taken as the smallest carbohydrate. If this is treated with periodic acid, it will be cleaved here, this carbon will get 1 more hydroxyl and will be converted into a molecule of formic acid. This lower carbon which has got 1 hydroxyl will get 1 more hydroxyl, then eliminate a water molecule and convert it into molecule of formaldehyde. This carbon will get 1 hydroxyl from this side, 1 hydroxyl from this side, will eliminate a water molecule and will be converted into molecule of formic acid. So, glyceraldehyde on oxidation with periodic acid will give us 2 molecules of formic acid, 1 molecule of formaldehyde. If we have a long chain, say 5 carbon monosaccharide like CHO, CHOH, 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 CH2OH, we will find that all those carbons which are present as CHOH will give us formic acid. This aldehyde carbon will give us formic acid, and this lower carbon which is present as CH2OH will give us formaldehyde. And this 5 carbon monosaccharide on oxidation gives us 1 formaldehyde and 4 formic acid. But this does not give us the idea about the ring size, because every bond will be cleaved whether it is open chain or cyclic. But again, this reaction was used for determining the ring size of glucosides. When this normal glucoside was taken and it was treated with periodic acid, it was found that 2 molecules of periodic acid are used up, and it shows, because if it is a 6-membered ring structure, only cleavage can occur here, the 2 carbons having neighboring hydroxyl each, and here also hydroxyl. So, cleavage can occur across this bond and this bond. This molecule should be lost as a molecule of formic acid, and these 2 ends will be converted into aldehydes, and we get this dialdehyde and a molecule of formic acid. Then the structure for this dialdehyde was further confirmed by its oxidation into carboxylic acids. These 2 carbons get oxidized into carboxylic acid, then it is treated with strontium carbonate, we get strontium salt, and then it is hydrolyzed and further oxidized to give these a 3 carbon dicarboxylic acid, a 2 carbon dicarboxylic acid, that is oxalic acid, and a 3 carbon carboxylic acid. So, using all these type of cleavages, structures were further confirmed that normal glucoside are 6-membered, and those glucosides which are obtained under cold conditions are 5-membered, like this. On cleavage on periodic acid will give this dialdehyde and a molecule of formaldehyde, because here the cleavage will occur, but no carbon portion separates. It is from this side it separates out, and then structure was further confirmed by the similar sequence. But none of these reactions could give the idea that what is the actual ring size in glucose. This could be determined only in somewhere in 1950, when we had different type of spectroscopic techniques, X-ray crystallography and some other instrumentation techniques, and it was found that actually glucose in the solid state exists mainly as 2 6-membered ring structures, this one and this one, alpha ionomer hydroxyl on the lower side and this beta ionomer, this hydroxyl on the upper side with a very small amount of open chain structure. But when it is dissolved in water, then all these 5 forms they coexist, and whichever reaction with particular reagent we carry out, if open chain form is used up in that, then cyclic forms they open up. If the cyclic structure is used, then open chain gets converted into cyclic structure, because they are all in equilibrium, and ultimately we get that product. So now we can say that glucose mainly is a mixture of all these 5 forms, but the major constituent in the solid state are 2 6-membered ring structures. Now, after that we talk about disaccharides. Till now we have been discussing about the monosaccharides. Now, disaccharides are those carbohydrates we have discussed earlier, which consist of 2 monosaccharide units. That is, they on hydrolysis give us 2 molecules of monosaccharides. Now, how these monosaccharides are linked with each other? Actually, these monosaccharides are linked by glycosidic linkage. We have discussed earlier that glycosidic linkage is formed when some alcohol or phenol combines with the anomeric hydroxyl. So, it is found that in disaccharides 2 monosaccharide units are always linked by glycosidic linkages. Now, we can show like this, that how glycosidic linkage is formed in disaccharides. Say this is a monosaccharide. I have taken a specific example, say it is alpha D glucopyranose. Now, this is the anomeric carbon. It can have hydroxyl on the lower side or on the upper side. If it is alpha, it is on the lower side. Now, another molecule of glucose or any other monosaccharide or any other alcohol which has this hydroxyl group can combine with this hydroxyl and can form the acetal linkage. And we have discussed that acetal linkage in carbohydrate chemistry is called glycosidic linkage. Now, suppose it is the another molecule of D-glucopyranose and it uses its hydroxyl at carbon number 4, and it reacts with it, eliminates a water molecule, and this ether type of linkage is formed. We call this as the glycosidic bond. But which side we will call the glycosidic bond? We will call the glycosidic bond towards that sugar moiety which is using the anomeric carbon, because this sugar moiety is using its alcohol part, is being used as alcohol. This is a glycone here, right, and glycoside is of this sugar moiety or this monosaccharide. So, this bond we will call as a glycosidic bond. Actually, this bond has been shown as a bent bond. Bonds are not like this, and there is no carbon at the corners. It is just an easy representation, so that you can understand that the hydroxyls at both the positions are downward and they have formed a bond here. How they are correctly represent, I will show. Now, suppose this is one monosaccharide, and I have shown in the earlier slide, this is another monosaccharide using the hydroxyl group at the carbon number 4. Suppose its hydroxyl is in the upward direction, then we can show the bond like this. Now, it is this sugar moiety which has now been converted into the acetal carbon, and this is the glycosidic bond. This is the A glycone moiety, although it is using the hydroxyl group from the 4th carbon. It will have its hemiacetal carbon free, means it can have its alpha or beta anomeric forms on this carbon. But there is a possibility that 2 sugar moieties may form this glycosidic bond using the anomeric hydroxyls. Then what will happen? Both will be converted into the acetal carbon. Now, this has been shown in the inverted way, because normal representation have the oxygen on this corner. This is the carbon number 1 now, and hydroxyl at carbon number 1 of this sugar moiety as well as hydroxyl at carbon number 1 of this sugar moiety, they have formed the ether type of linkage, that is a glycosidic linkage. So, both the carbons are now converted into their glycosidic form. Right. So, glycosides can be formed from two sugar moieties where both the sugars may be using their anomeric carbon, or one of the sugar moiety is being used as a hydroxyl group and other is using its anomeric carbon. We can show in a correct way using their conformations like this. Say this is sugar 1 and this is the hydroxyl group of the anomeric carbon. If it reacts with any other alcohol, it will form the glycoside and we will call this bond as a glycosidic bond. But if it reacts with another sugar moiety, let us say sugar 2, and it is the hydroxyl at carbon number 4 is being used as I showed in the previous slide, then we can correctly show the bond like this. This is the linkage between carbon number 1 of one sugar moiety and 4th of another sugar moiety. And now which bond is glycosidic bond? I am again repeating, it is the glycosidic bond where anomeric carbon of one of the sugar moiety is involved. This is not the glycosidic bond. So, this represents a disaccharide. Now, let us take up the example of some disaccharides. Maltose. Maltose is hydrolyzed with dilute acids or enzymes, that is maltase, to give us 2 molecules of D plus glucose. It means maltose consists of 2 D plus glucose units. It is a reducing sugar. Reducing, I think you remember we discussed earlier, those sugars are reducing sugar which reduce Fehling solution or Tollens solution, and for that they require the aldehydic group. If aldehydic group is not there, in the anomeric carbon should be in the form of hemiacetal, which opens up in the alkaline medium and we get the color change. So, this is the actual structure for maltose. In maltose, what we find that one D plus glucose moiety is linked to another D plus glucose moiety, and it is the anomeric carbon number 1 of this glucose that forms the bond with the carbon number 4 of this. The hydroxyl at carbon number 4 forms the linkage here. Now, this linkage we call it as alpha linkage, alpha glycosidic linkage. Why? Because this sugar moiety, this glucose molecule which is forming the glycoside is in the alpha conformation, the lower side. We call it as a beta anomer. Now, anomer is not on this side. Anomer will be named from this side where the anomeric carbon is having free hydroxyl. This can open up. If hydroxyl is on the upper side, it is beta anomer. If hydroxyl is on the lower side, it is alpha anomer. This I have shown here. This is the alpha anomer. This is the beta anomer, but the position for all other hydroxyl and groups, it remains the same. So, this is alpha linkage, here also we will call it as alpha linkage, right. Anomer of maltose is due to this anomeric carbon, where hydroxyl can be in the upper direction or in the lower direction in this Haworth projection. How to name these disaccharides? We name this disaccharide the one monosaccharide which has its open and the anomeric carbon as glucose or as monosaccharide. It may be glucose, fructose or whatsoever it is, and the other one as glucoside. So, this will be named like this, right. 4O, we are naming this as glucopyranose. This is our basic molecule, glucopyranose. At the 4th carbon, there is a hydroxyl group, and on that hydroxyl through oxygen, what is linked? This glucoside molecule. Now, this glucoside molecule is linked through alpha linkage and it is D-glucopyranose. Since it has formed the bond, it becomes pyranosyl. So, what we call as 4O means through oxygen is linked at the 4th position, and what is linked? Alpha D-glucopyranosyl. This represents the alpha D-glucopyranosyl, and then we call it as beta D-glucopyranose because it is a beta anomer and this is D-glucopyranose. Similarly, this will have the same name, only difference will be it is the alpha anomer here. So, we call it as 4O alpha D-glucopyranosyl, alpha D-glucopyranose. So, disaccharides are named like this. What we do, the one which has the free anomeric carbon that is taken as the basic sugar moiety, and the other monosaccharide is treated as it is formed the glycoside, and the number of linkage is shown by the hydroxyl group that is used in the bond formation. The correct conformation for maltose can be represented like this. This is the beta ionomer, this hydroxyl is going upward direction, this hydroxyl is in downward, and this is forming the alpha linkage, this hydroxyl is already downward. So, this shows the correct bond formed between these two sugar moieties. This is the carbon number 1 of this glucose, and this is carbon number 4 of this glucose, and alpha ionomer will have this hydroxyl downward, other things are same. Then let us take up second disaccharide, lactose. Lactose is present in milk and is a reducing sugar, again means it also has one anomeric carbon which is free. It is hydrolyzed by dilute acids or the enzyme lactase to give D plus galactose and D plus glucose, means this consists of two monosaccharides, D plus galactose and D plus glucose, and they are linked like this. It has been found that it is the carbon number 4 of the glucose moiety that is involved in the bond formation with the carbon number 1 of D plus galactose moiety, and this galactose is forming the beta linkage, means its hydroxyl is in the upward direction. So, again we show tilted bond like this just to represent the exact position of the bond, but the correct representation will be their Haworth projection, which can be shown like this, that this is the glucose moiety, its 4th carbon, the hydroxyl is going downward, and this is another galactose moiety, it is forming the beta linkage, its hydroxyl is upward. So, the bond is formed like this. Now, this is non-reducing half, obviously this is having the free anomeric carbon is the reducing half. So, it will act as a reducing sugar because of this carbon, and the conformations can be represented like this. This is the carbon number 4 of this glucose moiety, and this is 1 for the galactose moiety, and it will be named as 4O, that is the 4th carbon through oxygen. What is linked is beta D galactopyranosyl. This is the galactopyranose ring becomes galactopyranosyl, and it is the beta bond. So, beta D galactopyranosyl D glucopyranose, and again there can be alpha and beta ionomers on this carbon. Then the third disaccharide we take up is sucrose. Sucrose is hydrolyzed by acids or by the enzyme invertase, and sucrose on hydrolysis gives a mixture of a molecule of glucose and a molecule of fructose, and this hydrolyzed product is also named as invert sugar. Now, why we call it as invert sugar? Actually, when this reaction was carried out on sugar moiety, sucrose is the most common sugar that we use at our home, obtained from cane, that is cane sugar we call it. It is hydrolyzed and we get the product. Now, sucrose molecule itself is a dextrorotatory, and when it was hydrolyzed, the product which was obtained, it was levorotatory. So, just on this basis it was given the name invert sugar, as if some inversion has occurred. But later on, when the chemistry was known for this reaction, it was found that what happens, sucrose gets hydrolyzed, we get one molecule of glucose and one molecule of fructose. The optical activity for glucose molecule is plus 57.2 degrees, whereas the optical activity for fructose molecule is minus 119. So, net resultant is negative optical activity. So, by mistake this invert sugar name was given, but the name is still retained. It is not the sucrose molecule with inverted configuration. Honey is the most common example of invert sugar, and it is found to be non-reducing. So, when the structure was determined, it was found that glucose molecule and fructose molecule both are using their anomeric carbon for the glycosidic bond formation. This on hydrolysis gives 1 D plus glucose and 1 D minus fructose, and they are linked like this. This is the glucose unit, and it is forming the alpha linkage, that is hydroxyl downward. Now, this is the fructose unit. Now, when we discussed how to represent these 5-membered ring structures, you remember that we used that numbering is always from the clockwise direction. The carbon number 2 should have been here, but now this carbon number 2 is using the hydroxyl for bond formation, and I have to show it on this side. So, that is why we just invert the structure. I can show using my hands that how this inversion has been taken here. Suppose this is the normal representation for a molecule of fructose. This end represents the oxygen and this thumb is representing the carbon number 2 where the linkage is there. Just for showing the linkage, we write it like this. So, oxygen is retained at the same position, but what has happened, the carbon number 2 has come on to this side. Now, if the hydroxyl group at carbon number 2 was going upward, now when we write it like this, it will be going downward, and this is the situation here. Fructose is using actually its beta anomer, and at carbon number 2 hydroxyl would be, when it is here, it would be in the upward direction. So, when I have inverted it, this hydroxyl is now in the downward direction. So, and this hydroxyl at carbon number 2 of the fructose unit and carbon number 1 of the glucose unit, they form the bond here. This is now a glycosidic bond from this side as well as from this side, but from the glucose side it is alpha linkage, from the fructose side it is beta linkage. These honeybees, they have the enzyme, and when they collect this sugar molecule from the flowers, it gets hydrolyzed, and honey is mixture of fructose and glucose. And that is why in our Ayurvedic medicines also, when nothing was known, as a quick source of energy, all those Ved people, they were giving the medicines with honey, because honey has glucose and fructose which could be easily absorbed by our body. These days in our allopathic system, we introduce glucose through veins, but at that time those techniques were not available. Now, how to name this disaccharide? As I said, this sucrose is a non-reducing sugar because none of the anomeric carbon is free, so they cannot reduce, and when we try to name, we can name it now in two ways, taking base as a fructose molecule or taking base as a glucose molecule. If I take this fructose molecule as a base, I call it as alpha D glucopyranosyl. This is the pyranose molecule. So, alpha D glucopyranosyl, beta D fructofuranoside. Or if we take this molecule as the base molecule, we will call it as beta D fructofuranosyl, alpha D glucopyranoside. Only thing is that we must write correctly the linkage. Fructose is forming the beta linkage, whereas glucose is forming the alpha linkage. Then we draw this in the correct conformation. This is showing downward the alpha linkage, and this is the correct representation for the fructose, hydroxyl going at carbon number to the upward direction, and they are linked like this. This is the beta glycosidic linkage. Let us move on to polysaccharides. Polysaccharides are those carbohydrates which yield a large number of monosaccharide molecules on hydrolysis, and in our general life we deal more with the polysaccharide molecules. The common examples of polysaccharides are starch, cellulose, glycogen, and different gums which we get from plants. The two main functions of the polysaccharides are that they are the food storage or they provide structure. The most common polysaccharide which we use as our food is starch. It occurs mainly in seeds, roots, tubers from plants. Then it is a polymer of alpha D plus glucose. I mean, all starch contains only D plus glucose molecule and with the alpha linkage only. It consists of two types of components. They are called amylose and amylopectin. Actually, amylose is about 20% of the starch from most of the sources, and it is a water soluble constituent, whereas amylopectin forms about 80% and it is water insoluble. This amylose is a straight chain polymer which consists of about 200 to 1000 alpha D plus glucose units, and these glucose units are linked 1 to 4. That is, carbon number 1 of one glucose molecule is linked with carbon number 4 of the another glucose molecule like this. This is one glucose molecule, this is the hydroxyl at carbon number 4, this another glucose molecule, its alpha anomer is being used, so hydroxyl is in the lower side and they form this glycosidic bond. But its own hydroxyl at carbon number 4 forms the bond with another glucose molecule and a chain continues. So, amylose is a straight chain molecule in which a large number of these D plus glucose molecules are linked all through alpha linkages. We can show the conformational representation like this. This is the alpha glycosidic linkage for all, downward linkage. Right. Then amylopectin, which I said is about 80% of the starch and it is insoluble. It consists of about 300 to 6000 glucose units linked together. And again, the branching occurs and average number of glucose units per branch comes out to be 25 glucose units. Linkage is again alpha in all the cases. Then how they are linked? Some chains are formed by C1 to C4 linkage, and then some of the glucose molecules, they get attached to carbon number 6 of the glucose moiety. We can show like this. Say this is the straight chain of glucose as it was in amylose. This is carbon number 1 of glucose joined with the carbon number 4 of another glucose and so on. Now this is carbon number 6 CH2OH here, and one of the glucose molecule using its anomeric carbon, that is carbon number 1, forms a glycosidic bond here, and then again chain continues, and then some other position again a branch chain may start, a branching may start here and so on. So that is the structure for amylopectin. Conformational representation we can show like this. This was the chain as in case of amylose, but at carbon number 6 some of the glucose molecules may link and then another chain as a branch continues here. Cellulose. Cellulose imparts shape and structure to plants. Mainly plant material is cellulose. Cotton is pure cellulose which is obtained from plants, and it is present in the cell wall. Again, cellulose is also a linear polymer consisting of about 300 to 2500 glucose molecules. But the only difference from the starch is here the glucose units are linked through a beta linkage. That is, cellulose is a polymer of beta D plus glucose units. Now you see there is a very little difference between starch and cellulose. Cellulose has a beta linkage and starch has alpha linkage. Both are made up of D plus glucose. Our body has got no enzyme to break this beta bonds, beta linkages. That is why we cannot use cellulose as our food. Cellulose molecules acts as fibers only as a part of our food. But there are many animals, they have the enzymes, and the animals use the plant products as their food. We can take only starch as our food. Then we can show the bonds like this. This is one glucose molecule using its carbon number 4 hydroxyl going downward, and it is a beta bond in the beta ionomer of another glucose molecule, that is hydroxyl on the upside, forms a bond here, and similarly another glucose using its carbon number 1 hydroxyl with the bond formation with the hydroxyl at carbon number 4 and so on. So cellulose has beta glycosidic linkage between glucose molecules. We can show the Haworth projection for cellulose like this, that it is hydroxyl from the upper side and this hydroxyl from the lower side. And we can show the conformational representation for cellulose like this, that this at carbon number 4 the hydroxyl is going downward, and at carbon number 1 it is not going downward. Remember, this cellulose is represented in an inverted way. The hydroxyl is not here, oxygen, we have inverted it. So carbon number 1 is here, but the hydroxyl which was going upward is going downward. So this way we can represent the conformation for cellulose. Then the third, glycogen. Glycogen is also known as animal starch. Actually this is the way the carbohydrate is stored in our body and in other animals also. It occurs mainly in liver and muscles. It is a branch chain polymer, and the molecules are very large, 6000 to 30,000 D plus glucose units, and again they are having alpha linkage. The structure for glycogen is very much related to amylopectin. The only difference is that the molecules are very large and the branching is also very high. The average number of glucose moiety per branch comes out to be 12 to 15 glucose units. Then in our body, whenever we have excess glucose, it gets stored in the form of glycogen, and the process is called glycogenesis. But when we are not getting the food and our body requires glucose, then this glycogen breaks up to give glucose, and that is called glycogenolysis. So these processes of glycogenesis and glycogenolysis are constantly going on in our body, and we have the storage of food in our body in the form of glycogen. The structure for this starch and glycogen can be compared. Say this is amylose. This one small circle is representing one ring for the glucose, and then long chain is there. It may coiled up or it may form the rings, or different shapes it may be present. Whereas in amylopectin there will be branching at different places, and in glycogen more highly branched and larger number of glucose unit involved. Since here this structure is quite open and more of the hydroxyl groups are exposed, they can form hydrogen bond with water, and that is why amylose becomes water soluble. Whereas in amylopectin and glycogen, the structure is compact, lesser number of hydroxyl groups are exposed to water and they become water insoluble. Then very briefly I will talk about the sweetness of different monosaccharides which we have been talking about, because as I said in the very first session that those carbohydrates which are sweet in taste are classified as sugars. So starch, fiber, cellulose, glycogen, they are not sweet, so they are given a sweetness value of 0. But when we compare the sweetness of different monosaccharides or disaccharides, so sucrose is taken as a base, and if we give sucrose the number 100, then we find the glucose is less sweeter than this, it gets a value of 74. Galactose is even less sweeter, is 33. Fructose is the sweetest monosaccharide, it is about 1.73 points sweeter than sucrose, value comes out to be 173. Maltose is again 33. Lactose is very little sweet, which is present in milk, and slight sweetness of the milk is due to this lactose. On this scale it comes out to be 16. So this is all about the carbohydrates which I wanted to discuss. Now very quickly I will revise that what we have done in different sessions in carbohydrates. We discussed the classification of carbohydrates, that they are classified as monosaccharides, oligosaccharides and polysaccharides. Then we discussed that how the structure determination of monosaccharides was carried out, then their conformation, configuration, and then how they are represented in Howth projection, then their exact conformations are represented, and then how they combine to form disaccharides and polysaccharides. That's all. Thank you.
Thank you very much, sir, for a very insightful lecture. Definitely you have discussed monosaccharides and you have continued with the polysaccharides. Thank you very much, sir. Dear students, this lecture will be uploaded on the CEC page at the YouTube. So you can look up this lecture and follow up, and definitely send in your queries so that sir can answer your questions. Thank you.